Okay, then let's continue with the remaining of Voronoi diagrams. We discussed some simple theorems regarding the Voronoi diagrams. If you remember, the last theorem was about two properties for this given Voronoi diagram. The set of points actually satisfy these, let's say, properties. What are they? The first one is that if there's a point Q, and if it's the vertex, if it's going to be a vertex of the Voronoi diagram, then that means the largest empty circle around this point or the vertex Q should have at least three sides, and it shouldn't have any, let's say, inside. This is the requirement. There should be at least three sides on this largest boundary. It cannot have just two. And obviously, we disregard the degenerate cases. For instance, the case where you have, let me draw the sides on the same line. I disregard this one since it's a bit tricky. We are just considering the general case where you distribute these Voronoi sides such that you don't have any three on the same line. So what is the second requirement, second property? It's about the bisector or the edges. And if, let's say, point is on the bisector, and if you have such a circle and this circle has just two sides on the boundary, then we can say that it's part of the Voronoi edge. But if it has three of them, then we say that it's a vertex. If the largest circle around this point has just two sides, then we say that it's one of the edges of the Voronoi diagram. Now let's continue with some of the important issues. If you remember the first observation, it was about the intersection of half planes. We had such, let's say, Voronoi diagrams kind of things. And we said that by checking the Voronoi diagrams, checking the relation between the sides, you may have some half planes. And if you take the intersection of these half planes, then you may find a specific cell in that Voronoi diagram. And it's simply the common intersection of, again, half planes. As we discussed in the linear programming chapter, we can easily find it in linear arithmetic time. But this is true only for a single set. So if you want to determine the whole Voronoi diagram, then you need to have n number of this operation. So that's why we simply multiply with n, and we have such a higher time complexity. So this is quite high, and we should find a better way to complete the whole Voronoi diagram once you are given some number of sites. Any questions, guys, up to this point? So now what we are going to do for this better algorithm, for this faster algorithm, as in the previous chapters, we will have a sweep line. And this sweep line will go through, assume that these are some Voronoi sides on the plane. Again, we will have a kind of a sweeping line. This line will start sweeping from top to bottom, and during this movement, it will compute the Voronoi diagram on the fly. So once this line is around here, then that means we are done with this algorithm and the Voronoi diagram of these sides are computed. So the thing is that while we are moving this line, sweeping line downwards, we should always keep this information up to date about the Voronoi diagram, as we have done actually in the previous sweep line algorithms. But obviously, similar to the previous ones, at some point of this movement, we will stop and do some operation, do some computations, and you know that these points are simply called as event points. And here you see, for instance, an example, our sweep line started from here, from top. While it moves downwards, at some event points, it performs some operations, and now you can see at this point, it's already computed this part of the Voronoi diagram. This part is completed already, but these dashed regions, dashed lines are not completed yet. And while if you continue this movement, they will be completed in a moment. And a different thing in this algorithm is that, as you see, we have some kind of arcs, some parabola around here. We will discuss them. This is the main difference if you compare with other sweeping algorithms. We have a kind of a beach line. We have such parabola. We have the intersections. These intersections are quite important. We will discuss them in a moment. But this is the fundamental idea. While moving downwards with a sweeping with an imaginary line, we do the computation on the fly. Now I will show you an example. Let me open this website. Yep. Share view. Okay. Now I think you can see this website. It's a very nice one. We will see how these things are actually completed. Now let me randomly put some points. Okay. You may put as many as you like. Okay. Now click next. As you see, this is our sweeping line. As it moves, it computes all these Voronoi edges, Voronoi, let's say, vertices. I think it had a kind of a problem here. It couldn't continue. Let's restart it. But I will now simplify it. I think it couldn't finish it. Let's have less number of Voronoi size this time. You see some arcs are generated. These blue ones are the Voronoi edges, Voronoi vertices, and now it's finalized. So this is how we are going to draw a Voronoi diagram for a given size. And let's redo it, and I will slow down a little bit. You see we have new size. Once we have new size, we have some arcs generated. And now you will see that a new parabola will appear here. Oop. We have 3 parabolas here at this point. And sometimes these parabola may disappear. So these are the kind of events actually we will consider. And as you see, it's drawing kind of circles since as we discussed in the slides, we have some rules related with the Voronoi diagram. The vertices, the minimum largest, let me try to draw a kind of a circle here. Draw a circle. We move it. No, I couldn't have done it. Redo, oops, undo, sorry. Let me, okay, I think that might be, it's not moving, so let me clear and draw with my hand. Now I'm just focusing on this vertex here. And if you look at this empty largest circle, it's not a circle, but assume that this is a circle. It can have at least 3 or more sides. It cannot have just 2 sides if it's a vertex of the Voronoi diagram. But if it's a simple, let's say, point on the edge, then its largest empty circle will have 2 Voronoi, let's say, size. So these are the main rules of the Voronoi diagram, and we will discuss now details of these issues and try to come up with a nice algorithm. Any questions, guys, about the this website, about how we actually construct it? Right now, you don't know about the details, but in a moment, you'll be focusing on them. Okay, here we continue with the slides. So as you have seen on the video or on the animation, it's not easy actually to do such computations in a proper way, but we will come up with a nice algorithm. The important thing about this sweeping line this time is that the part of the Voronoi diagram above this imaginary line L depends not only on the sides that are above the line, but also it depends on the size underneath the sweeping line. So this is a new thing if you compare with other sweeping line algorithms. So the size underneath this line are also contributing to the Voronoi side, which we have computed actually before. So this is an important issue regarding this algorithm. Okay, so we always, while doing this, while implementing this algorithm, we need to have proper data structures, and in these data structures, we need to store these actually arcs, and we will maintain the information related to these arcs, and also we need to have another data structure for the Voronoi diagram. We should keep these edges, the vertices. Now we'll be going into details. So here comes the question. What is the part of the Voronoi diagram above this imaginary line L that cannot be changed anymore? If you look at here, for instance, this part cannot be changed. It's finalized, but this has not been finalized. It may be modified, and which means that this part, this edge actually depends on the size underneath. Since we are not aware of the size, we may have, for instance, some number of sides here, and these may affect this dashed region. This is not finalized yet, but the upper part, this region, has already been finalized, and so we can simply store them as the Voronoi diagram into our proper data structures. So the thing is that we have some requirements. The distance of point Q, which is actually a member of L plus, which is the region actually we covered. Assume that you have kind of a point here. This is Q. If the distance of this point to any side below L, let me draw this distance. This is a side below L. If this distance is greater than the distance of Q to the L itself, this is L. Yes, this is it actually. If this is greater, then we can say that this is finalized and we are not going to change anything. But if you look at other points, that will not be the case. Another issue, the locus of points that are closer to some site, let's say PI, which is a member of this upper region, then to L is bounded by a parabola. So let's have a look at a point here, or assume that this is another point, let's name it as M, and assume that this is PI, this Voronoi site is named as PI. So the locus of points that are closer to some site, these are actually the locus of points which are closer to PI than their distance to actually L. If you compare the distance of this point to L and its distance to PI, that should be the same. So that's why this is the locus of the border around this Voronoi site. So the upper of this border, let's say, belongs to that cell, but we are not sure about the below region of these parabola or the border. So this is the main thing. The locus of points which are closer to PI will contribute to this parabola, and it's any, let's say, if you focus on a single point, this distance of M, let's say, to pi is equal to the distance of M to L. That should be the same, since they are on the boundary. But any point inside this region will have less distance to the side than its distance to the sweeping line. So that's the main thing behind the parabola. And with the help of this fundamental statement, we will draw all the parabola around the Voronoi size and try to actually come up with the whole Voronoi diagram. And questions, guys, regarding these issues? These are the fundamental things on the Voronoi diagrams. Make sure that you are comfortable with these statements. Otherwise, in the next slides, next theorems, things may get complicated. Okay. We said that the locus of actually points which are closer to the sides above our imaginary line L than to L is bounded simply by parabolic arcs. You see we have some of them here, another portion. So we have some connection points. So another one here. So how many of them we have? 1, 2, 3, 4. We have 5, let's say, parabolic arcs. And if you look at the number of Voronoi sides, we have 1, 2, 3, and 4, but we have 5 of them. So there's a kind of a relation, but it's not always a requirement that the number of sides should be equal to the parabolic portions. Since if you compare here, for instance, the second and the fourth are part of the parabolic arc around this Voronoi side. And this third portion is related with this one here underneath. The first one is related to this one, and the fifth one is related to the one here. And the whole part, this whole, let's say, set of parabolic arcs is called as a beach line. And this is a term we are going to use in the rest of this chapter. And if you look at the details of it, our beach line actually passes through the lowest point of all the parabolas. So this is the complete parabola, but we are only passing through the lowest portion of it. And it's also the same for others, but for this one, it's a bit weird. We have 2 portions of it, but at least we are again on the downward region of the parabolas. The upper regions are not important. Now we have another observation, a very simple one. The beach line is x monotone, which means that any vertical line actually intersecting this beach line will only have a single intersection. You see, we don't have double or 3 intersections. We only intersect with the beach line just once. So that's why beach line is an x monotone, let's say, kind of function or curve. And on these beach line, the breakpoints are the most important regions. This is the breakpoint, another breakpoint. And why they are important? Since they are kind of drawing this Voronoi diagram. Okay. If I draw a little bit above, let me try to make it. Yes, this is just while our sweeping line is just above this current position. Okay, this is, let's say, L prime, and this is the resulting beach line for L prime. And here you can see again our breakpoints are on the Voronoi edge, since they are responsible for drawing the edges of the Voronoi diagram. So while we are moving our sweep line downwards, these connection points or the breakpoints are drawing the edges of the Voronoi diagram. Any questions, guys, about this issue, the importance of breakpoints? So in the computation, actually, we need to actually determine these breakpoints and should actually consider their movements, since they will be tracing out the Voronoi diagram. So what we do in our implementation, as opposed to the different sweeping line algorithms, in the other ones, if you remember, we were always maintaining some information related with the intersection of the sweeping line. But this time, it's not important for us. What we are going to maintain is that the status of beach line. So which parabolas are contributing to this beach line will be our main consideration, and they will be stored in a special data structure. But now let's focus on how we have some changes on the beach line. There are two issues. You may have a new arc generated, a new parabolic arc. For instance, we may have another one here, like this one, a little one. Or we may have an arc actually disappear. So we only have two cases, two events for these arcs. A new one may appear or an existing one may disappear. And it was also the same in the animation, if you remember, for the new size. We have some arcs generated, but at a point, these arcs were disappeared. So I can say that we will need to have for sure a kind of an site event. So sites are important. When you come up with a site, there needs to be some computation. And this computation will be about adding a new parabola to our beach line. So here you see an example. We have our imaginary sweeping line moving downwards. We have this 3 Voronoi size. And once our sweeping line meets this Voronoi side, as you see, we will have a kind of an edge generated first, and then this edge will be an arc while we move our actually imaginary line downwards a little bit. So this is how a parabola appears in our sweeping line approach. And at this point, obviously, we will have a kind of an, as I said, this can be considered as a line, or you may also name it as a parabola having just a 0 width. And as you go downwards, obviously, the size of our parabola will be getting larger. So now let's continue with again the site events. And if you remember in the previous slides, we said that the breakpoints on these parabolas are highly important. They are tracing out Voronoi edges. And if you look at here, for instance, once a parabola is actually introduced into your beach line, what happens? At first, you will have a single breakpoint, but as your sweeping line moves downwards, we will have 2 of them. And they will be tracing out simply the Voronoi diagram. So the edge of the Voronoi diagram. So their movement is an important issue for our Voronoi diagram, and we should be aware of it and try to have a kind of an proper data structures. I'm sorry, guys. Any questions at this point? Okay, let's continue. And I said that these breakpoints are highly important. They are tracing out the Voronoi edge. And this is the thing we discussed. At a site event, we will have 2 new breakpoints appearing. At first, they will be exactly the same point, but as you go downwards, they will be tracing out the Voronoi edge in opposite directions. So do you think, can we have another possibility for a new arc to be appearing on our beach line? Obviously, no, we don't have any other options. We can only have new arcs generated just with the help of a site event. So This is the only event we can have for a new arc generated. So that's actually summarizes our lemma 6. The only way in which a new arc, this is for instance the new arc here, can appear on this beach line is through a site event. We cannot ever have any other options. Now let's focus on the second event. This is called as a circle event. It's a bit different, but related again with the parabolas. This time, if you remember, while we are moving our sweeping line, we said that sometimes an arc appears, and for other times, we may have these arcs actually disappear. So this circle event is related with the arcs disappearing. Here you see an example. We have 3 Voronoi size up to this point, up to this level. We have these edges of the Voronoi diagrams actually drawn. But now, once our sweeping line moves a little bit, you will see that we have a specific point Q, and this point Q is actually kind of a center of a circle. And this obviously have the same radius r, and the distance of this Q to the sweeping line is also equal to r. This is r. So if you remember, one of our properties we discussed for the Voronoi diagrams is that in the Voronoi diagram, if you have a vertex, if you have a kind of a corner point vertex, that the largest empty circle of this vertex should have at least 3 Voronoi size on the boundary of this largest circle. And that's true here. We have another extra, let's say, requirement. The radius or the distance of this vertex should be the same. The radius of this circle should be the same with its distance to the sweeping line. So here is true. So we can simply say that at this point, the arc here, alpha prime, will be disappeared, and we will have just a single, let's say, vertex. Another issue is that initially we have 2 breakpoints, right? But right after this circle event, we will only have a single breakpoint, and this, at least in this portion of the Voronoi diagram. Here's illustrated again. This is the same things we discussed. Yes, it should be the point Q is equidistant from L and all the other sides, all these 3 sides on the boundary. So if you have such a case, then we can say that it's a circle event and vertex is generated for the Voronoi diagram. If you look at here in the initial part, we don't have any vertex on the Voronoi diagram, but once we come up with a circle event, vertex for the Voronoi diagram is generated. So another issue, we know that we cannot have another size inside the circle. So it's not possible. If you have it, then that means you have a problem. You have done something wrong, and you should start your computation once again. And that point, obviously, Q will be the vertex of our Voronoi diagram. So now we have another lemma regarding this circle events. The only way in which an existing arc can disappear from the beach line is through a circle event. We don't have any other way. So if we summarize, at the site events, we have new arcs appearing, and that means a new edge will start growing in the Voronoi diagram. But for the circle events, we'll have arcs disappearing, they will be dropping out, and they will form a kind of a vertex of the Voronoi diagram. So this is a summary of the events we need to handle. Site events are related with new arcs, and circular events are related with disappearing arcs. So this is actually how we are going to implement the algorithm. We need to consider these events while we are sweeping the plane. But obviously, in the implementation part, we need to have proper data structures. Now we will briefly talk about them. The first one is about a data structure which is responsible for storing the whole Voronoi diagram. And for that purpose, we will see that kind of a double-edged list will be used, but for the rest, for the other part of the sweep line algorithm, obviously we need to have an event queue, and in this queue we will store the events after each other and then handle them one by one. Another data structure we need to have for the sweep line algorithm is that while you are moving again, you need to keep the status of the sweep line and also the beach line. So you need to again have some special data structure for that. So let's have a look at the first one. The first one was about the Voronoi diagram itself, the computed Voronoi diagram. So what we need to have, we didn't discuss this type of data structure, but let's take it as granted. This is called as doubly connected edge list. And in that kind of edge list, we have an information related to the edges. So it will have a kind of a direction. Also, we will store it in the reverse direction. And in addition to these directions and vertices, we need to also store this bounding box. So what happens if you don't have a bounding box? We know that these lines will be going to infinity and they will be considered as half lines. So in order to make it simpler and implementable, we need to have a kind of an bounding box around our, let's say, Voronoi sites. So here is the doubly connected edge list. And this data structure is a bit complicated. I don't want to go into details, but here you see we have the origin, we have the twin of the line, we have some incident faces, which is the face we are dealing with, the next vertex, the next edges. So they are all stored, and if you have it properly, you can compute any kind of complicated, let's say, such edge, let's say, following implementations. So another thing, if you remember, we said that for the sweep line algorithm, we need to store the status of the beach line. And for that purpose, we'll be using a balanced binary search tree. I think you remember balanced binary search trees. We shouldn't have too much level differences between the leaves. We can have at most one level difference between the leaves. So the leaves are important in balanced binary search trees, and in this case, the leaves will actually be referring to the arcs of the beach line. So let me have a kind of an balanced binary search tree here. It doesn't have to be just, let's say, binary, but in some cases you may also have ternary. But the thing is that if you remember, you need to have at least at maximum one level difference between the leaves. You see here, for instance, we have 4 of them, and we only have a single level difference between the last one and the remaining ones. And these leaves will refer actually to the arcs we have in the beach line. So this might be the rightmost leaf, leftmost leaf, and once you have proper information, kind of pointers in these leaves, then you may refer to some other values, some other data structures, and try to do some computations and determine the vertices or the edges of the Voronoi diagram. And the internal nodes of this balanced binary search tree will include actually the breakpoints, of the beach line. So this is another important issue. The breakpoints will be inside the internal nodes. And on the leaves, we are referring to the arcs, but not actually the breakpoints. Breakpoints are stored in the internal nodes. Since it's a search tree, a binary search tree, all these computations, all these search operations can be done in logarithmic time. As I mentioned, we may have some extra pointers in this data structure so that we can refer to other data structures easily and try to complete our Voronoi diagram in a shorter time. So the other data structure we need to have in the pipeline process is the event queue, and this will be a priority type of queue. The items in the queue may have actually different priorities. So depending on their importance, you may handle them first and then the other one. But the main priority will be according to the y coordinate. The ones having higher y coordinates will have the highest priority. And this actual data structure will be storing the upcoming events, which are already known. So for the site events, we can simply store the information related with the site, simply the coordinates. But for the circle events, we will need to store the lowest part of the circle, since at that point, the vertex will be generated. If you store some other portions of the circle, it will not be meaningful, since for the vertex generation, the lowest part of the circle is responsible. We have another lemma. So actually it's somehow related to the circle events. Every Voronoi vertex is detected by means of a circle event. And we can say that all these events should have been actually handled, and the event queue should be empty once you have completed all these Voronoi diagram. And once you have done all these, once you handle all the events, then you will have this data structure empty, but have a kind of a beach line still existing. It may not disappear, and at that point, this means that you are going to have some half infinite edges. So if you do not have an bounding box, then you need to represent half infinite edges. But if you have a bounding box, then you may have simply the intersection of this half infinite edge with your, let's say, bounding box, and just store this part into your Voronoi diagram data structure. So how we do the algorithm, how we complete this Voronoi diagram? We will now go into details of it. The input is not that complicated, as you know. We only have the site of the Voronoi size. It's a kind of a point set on the plane, and the output obviously will be a Voronoi diagram. And in the previous slides, we discussed that for this Voronoi diagram, we are using a special data structure which is named as doubly connected edge list, and this D will be representing our Voronoi diagram. So what we do in this algorithm, we first kind of have an event queue. It will not be empty, since we know all the sizes is given. These are the inputs, and we can simply store them into our event queue. It will be they will correspond to the site events. And then we will have another data structure, an empty one for the status of the beach line, and an empty double connected edge list. Since we haven't computed anything, the output will be empty. So what we do, we continue handling our events actually, and we will do these operations, the upcoming operations, until all these events are handled. So what we do next in this while loop, we simply remove the largest, actually the most important event from our queue, and then handle it. If it's a site events occurring at a site PI, we call a specific function, handle site events. And this function will handle the event and then go back to here once again. Or if the event is a circle event, and then we will call handle circle event gamma. And obviously this gamma will be one of the leaves, which are actually representing a kind of an arc about to disappear in our status. Since if you remember the circle events, In circle events, we have arcs disappearing from our beach line. So then what we do next, if you are done with all the events, if you have completed site events and circle events, and still have left some actually beach line on your status data structure, then that means you'll have half infinite edges, and depending on the case where you have bounding paths or not, you may need to handle these last lines. And the last operation is for double connect edge. This is not as important. You need to traverse the edges so that your status data structure, your not the status, but the double connect edge data structure will be finalized, and you will simply output this Voronoi diagram.